Okay, maybe you can explain before we start. You can say something in general. So I have a very vague memory of this minimal circuit size problem. But I remember something like this, that there are pseudo-random functions which are behave as random functions but are simple. So if we can distinguish between a function with a large circuit and small circuit, then we can distinguish between pseudo-random function and random function, and then there cannot happen one-way function is impossible, blah, 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 blah. Something like this. So first, what of this is true and what of this is my false memory?
No, you said it exactly right. You said it exactly right. So, so this, if you could actually compute the size of the circuit, like I give you a truth table and you can compute the size of the circuit, then there would be no pseudorandom generators. Well, at least no pseudorandom generators. Yeah, that's it, right? Because the pseudorandom generator.
With what you will tell. That's, you want to prove that not only there is no one-way function, but something is NP hard.
Right, indeed. I'd like to prove. Well, I'd like to prove. Actually, I'm not even sure it's true. I'm totally on the edge on that one. But so you can define this problem, which is computing the size of the small circuit of a given truth table, and a question is whether this problem is NP hard.
But in the title, you say that it is. Yeah.
That is true, but only for functions that have multiple outputs.
With multiple, okay, so with function with multiple outputs, it's true, and for function with one output, it's just unknown yet.
Indeed, yeah.
But the fact that it cannot be polynomial unless there is no one-way function, it was known because of this pseudo-random thing.
Yes.
But no NP hardness, and now there is NP hardness.
No, well, there's NP hardness for multi-bit output, but it's very different. Like one of the things that you kind of see is that you use some dirty tricks that will actually.
So you don't use any pseudo-random construction, something completely different.
Right. Sorry, pseudo-random construction?
No, you construct a pseudo-random function, Bloom-Micheli pseudo-random function from. Which are indistinguishable from random functions or strings, which are just this pseudo-random generators. That's, you have a small seed, you get a large string, and you cannot distinguish from a random string, or you can get a function, you cannot distinguish from a function. So it seems that you prove stronger result but even maybe for this multi-output, but it's stronger result that they what they do. So what you say, it's a completely different technique, which is independent with what they did.
Can someone explain why, if we can compute the circuit size, then there are no pseudo-random generators?
No, no. I can only say something which I remember vaguely, but not really. So imagine there is a construction of a random function. A random function takes a seed and construct, and then you can compute a function, and then this function is indistinguishable from a random function.
Okay.
So if you have a short seed, then this function is computable by a small circuit with some parameters. I don't remember anything about the parameters. But if the function is generated by from a small seed by a simple circuit, if I remember correctly, this means that the function has small circuit itself.
Right.
And a random function doesn't have small circuit. So if we can separate one case from the other case, then we can distinguish things which should not be distinguishable.
Right.
That's my very imprecise understanding of what people do, what I read somehow, and what people told me somehow. But I cannot say exactly what are the parameters and what you can achieve. But it seems this argument should give at least something with some parameters. And what is Bruno saying, that he proves much stronger thing, that he proves that something is NP hard. And what I was asking, how it's related, it's completely new, different, more powerful technique, or you improve the previous one, or what is the connection between these two results?
Wait, so that's a good question. So the fact is that, so what we prove is that it's hard to distinguish. So you give me a truth table of a multi-output function, and it's hard to tell whether it comes from a small circuit or not.
Yeah.
Well, it's hard, actually, not exactly. It's actually hard to compute the exact value of the
Okay, so you have the more restricted thing. You just distinguish. You compute the exact value.
Already that is incomparable with the result that you're saying, right? Because you will be able to.
Of course, they are incomparable. You have a multi-valued output and you have exact value, but on the other hand, you prove NP completeness, not the non-existence of one-way functions. No. But since the philosophical meaning is somehow very close, that something is difficult, but of course there are variations. So I was just curious whether there is some connection between tools, or it's completely new approach, or you do some improvement, or what?
So the thing, I think that, I don't know, there's
okay,
something.
Now it's 5:10. So my internet, we can switch to real things. We don't need to.
Well, there will be some connection. So there's a connection with natural proofs, which is kind of how I came to this, which is related with this.
Let's see.
With this breaking of pseudorandom generators. So I guess we can start.
Yep, let's start.
Let's just do that. Okay. So I will talk about this NP hardness of circuit minimization for multi-output functions. And I should start by saying this is joint work with Rahul Ilango, who's a PhD student of Ryan Williams at MIT, and Igor Oliveira, who is now recently hired at the University of Warwick. So let me just, for those who did not follow that, so what's the MCSP problem? So it's the following computational task. I give you as input a Boolean function f. So let's think that f is an n-bit function, and I give you a number s. And the Boolean function should be encoded as the truth table, meaning it is.
So the input size is 2 to the n.
Indeed, n. The input size is 2 to the n for f. And I also give you a number s, and I'm asking you to tell me whether the size of the smallest circuit for f, the smallest Boolean circuit, is at most s. Okay, so that's kind of the vanilla MCSP problem. And it's trivial to see that MCSP is an NP because a witness that this is the case is the circuit that computes F. I can always guess it, and I can just check if it actually works. And the big open question in this that pervades all this work that I will talk about is whether this problem is NP hard, and that is really not known. Okay, so this, it seems very hard to tell. I mean, many people conjecture, or some people conjecture that this problem is NP intermediate, that it's not going to be NP complete. But one thing you can try to start with in order to kind of attack this problem is look at variants of the problem. So one variant would be whether you don't want to maybe know whether the size of f is at most s exactly, but you'd like to distinguish the case where the size of the small circuit for f is much smaller than, distinguish whether it's much smaller than s from the case where it's much bigger than s. It must be hard of approximation. You could look at, instead of like size of the small circuit, you could look at, size of the smallest formula, size of the smallest protocol, communication complexity, size of branching programs, combinatorial measures, such as discrepancy or rectangle bounds or whatever. Bounded depth circuits such as AC0, TC0, and so on. you could look at other kinds of tasks instead. Say, you know, so maybe you want the circuit, size of the small circuit, not that it computes a function, but maybe it agrees with some partial function on its domain, or which solves a search problem, or in the case that we're going to see today, whether it computes simultaneously all the bits of a certain function, generates some distribution, and so on. And you could think of whether this problem is NP hard under different kinds of reduction, many one reductions, Turing reductions, randomized reductions, and so forth. Okay. It's like this. So this is like
there's a variant to find out whether the Kolmogorov bounded time Kolmogorov complexity of something is smaller than something.
Yes.
Also a type of.
Yeah. So you can think this complexity can definitely be like Kolmogorov complexity, time bounded Kolmogorov complexity, and in effect, I mean these are very much related. Yeah. And when I talk about this, I usually call it meta complexity, because you're trying to understand what's the complexity of computing the computational complexity of a given problem. And so I was aware of this problem vaguely in the background, but I can say a little bit about how I actually started working on it. Like all sad stories, it starts with trying to prove some circular bounds. And then, you know, I was thinking of the thing like in very general terms. I was looking like at all the proofs, not just circular lower bounds, kind of all the lower bound proofs that I knew, and how do they work, and what's you know, many people have done this, and one such pair of people was Razborov and Rudich, and they kind of observed that many proofs at the time, or all proofs at the time, still most proofs today. So suppose you want to prove that a function f is not in the circuit class C, and you call this proof that f is not in C, you call it natural. If you can extract from the proof some kind of property of functions, and this property, if it's true for a certain function g, it should imply that this function is not in your circuit class. This property should be efficiently computable. Like if I give you the truth table of the function, you should be able to tell in polynomial time, say, whether the function has the property. And this property should be true for some random function g. And Razborov and Rudich showed at the time kind of that all the known circuit lower bounds were proven by natural proofs, like all the lower bounds for non-uniform, all the non-uniform circular bounds. And of course, but the key takeaway is that if you prove, if you construct an explicit function which doesn't have polynomial size circuits using a natural proof, then you would be able to break all pseudo-random generators in the way that Sasha has just kind of outlined. Because of course, if I give you the truth table of a pseudo-random generator, then the property will be true, but no, sorry, if I give you a pseudo-random function, the property will be true, but if I give you a pseudo-random generator, this function will be computable in your class C, and then the property should be false. So, but this kind of, you know, maybe 2 years later, after this paper came out, Raz and McKenzie have proven like what is maybe one of my favorite results in all complexity theory. It was kind of a technical thing. So they separated the monotone NC hierarchy. So if you take circuits that have ands and ors, but no negation gates, and you look at the classes of monotone functions that can be computed by polylog depth, it turns out that you can compute more at log to the I+1 depth than you can at log to the I depth. And it's kind of very impressive results. One of the very impressive things is that the proof is not natural. And so, you know, maybe you could see it as some kind of hope that you could maybe use it. And I've tried to prove non-monotone lower bounds. Even then, although this proof is not natural, it's still the case that every single lower bound proof that I know of against the complexity class C, and let's think of like combinatorially. So maybe this isn't true for diagonalization, but like every other proof that I know. Let's think of circuit complexity, communication complexity, anything like that. from the proof, you can actually extract some sort of property phi, which maybe isn't natural, but it does, it's a property that implies that the function is not in your class. And maybe it will not be true for a random function. So maybe it will only hold for a certain structured functions, and maybe it's not in polynomial time, but it's certainly in NP. And what this means is that kind of every lower bound proof that I know goes about by constructing a notion of some sort of short witness of hardness. So it's some kind of object that testifies that the function is not in your circuit class, or is not in your communication complexity class, or something like this. And so to recap, so every lower bound proof that I know kind of has this form or this structure. And in fact, Ryan Williams has shown in 2008 that if you want to construct, if there exists a function f which is in non-deterministic exponential time but doesn't have polynomial size circuits, then there will exist such a property phi which separates f, which phi which implies that, which is true for f and is computable in NP. So in some sense, at least in some cases, this kind of notion, this kind of existence of an efficient short witness of hardness is actually necessary in order to prove a separation. And so at the time, I was kind of thinking, and I think this is kind of a natural question, at least if you arrive at it from this direction, is there such a universal notion of witness of hardness? So and I guess maybe every complexity theorist's wet dream would be, we would like to have some property phi, and I could compute this in polynomial time. And if I give, so it's a function phi which accepts some parameter s, say, and some Boolean function f, and maybe some witness w. And if the circuit complexity or computational complexity under some measure of f is high, so if f has high complexity, then there will exist some object w which is comparable to s, which will witness this fact. However, if the complexity of f is low, like really low, then no matter what witness I give this verifier, it will say that this is not the witness of hardness. And why is this something that would be very, very nice if we had it? Is because if we knew what this, if we could construct such a phi, then we would know what a lower bound looks like. If you want to prove a lower bound for this C size measure, then you have to produce this object. That's what the lower bound would look like. And then we could actually go about trying to find that object. But we actually currently have no idea how a lower bound proof looks like for most classes. But it turns out that when you frame it like this, solving this problem, finding such a phi, is actually just asking whether some approximation version of this MCSP problem is in co-NP, right? So if the complexity is less than S, then it should be true that for every witness, this guy is 0. And if the complexity is high, then there should exist a witness. So it's like asking whether this version of MCSP is in co-NP. And of course, if this problem, this MCSP problem is NP hard, then you can say, well, no such universal notion of witness of hardness can exist unless, of course, NP is co-NP. And this was kind of how I came to the problem, because I was actually just thinking, can you actually make such a universal notion? And I realized, no, well, if this problem is NP hard, then you can't, and that's it. And that's, okay, so there's also some generalization of natural proofs saying that you couldn't have such a phi, such a notion of witness of hardness, if you can fool certain co-NP-like tests. If there exist pseudo-random generators that fool co-NP, basically, that's more like it. And but God knows if that's true, right? Maybe there isn't. Maybe that's not true. Actually, I'm on the edge on all of these questions. Okay. So, so I started working on this MCSP problem, and I managed to prove that it's hard to it's NP hard to compute for a partial function, but not if you give the truth table, but if you only give the set of pairs XFX for X in the domain of the function. And I had some other results on communication complexity. They weren't quite as interesting, but when I sent the paper to a bunch of people, it turns out that Rahul and Igor had this result for multi-output functions. And although their result is much more interesting, and this is what I'm going to present today, they generously let me be part of the paper. And so we put our results together, and we have this paper. Okay, so let me just say a bunch of things that have been proven. There's more work in this area, but kind of the more interesting results are the following. So there's some NP hardness results that were known for weaker classes of circuits, namely DNFs. So it turns out that if I give you a total Boolean function, I ask you what's the smallest size of a DNF that computes this function, this size is actually not just hard to compute, but even hard to approximate. And you know, this hard to compute was known since '79. It's a result by Mazek. And then in 2008, 2 independent papers proved that it's hard to approximate and gave simpler proofs than the original. This was improved by Hirahara, Oliveira, and Santanam in 2018, showing that, you know, finding the smallest DNF of XORs is also NP hard. And, oh, and I should have added it because I forgot to add it, but I'll just say, there's an upcoming paper by Rahul Ilango showing that it's even NP hard to compute the size of the smallest AC0 circuit of a fixed depth D. And that's a really beautiful paper. I've seen the proof, and we all can look forward to that paper because it's really nice. So I'm advertising it here as well. So some other results I've been showing is that, well, maybe you don't, you know, like as a build-up to show that MCSP is NP hard, you could show that it's hard for classes weaker than NP. For example, it's known that MCSP is NC1 hard under AC0 reductions. And I don't know why I didn't put the name of the people here, but I forgot. I think Allender is one of these people who've proven this. So no, if MCSP were in NC1, then, I'm sorry, if it were in AC0, then AC0 equal NC1. And it's known to be hard for a class which sits somewhere between P and co-AM intersect AM, so it's morally co-NP intersect NP. So it's known to be hard for this class called statistical zero knowledge. So you can actually, for instance, compute graph isomorphism if you have an oracle to MCSP. And this was proven by Allender and Das in 2014. And okay, so another line of work is kind of showing that this actual problem is actually not NP hard unless your reduction is somehow sufficiently strong. There's some paper by Murray and Williams that shows that if you have just a projection, for instance, just take the bits of the input and put them in the output, then it's not NP hard. And there's several results showing that if you manage to prove that this MCSP is NP hard under kind of not so weak, but still somewhat weak reductions, then you will prove you'll derive some major consequence, which we don't know how to prove. For example, if MCSP is NP hard and the deterministic polynomial time many to one reductions, then it would follow that X is not contained in BPP. So if you want to prove this, along the way, you have to prove that X is not contained in BPP. Okay, right, so what do we prove? We prove that the following problems are NP hard. So suppose that I give you a total multi-output Boolean function. So I give you some function f takes n bits and outputs m bits, and I give the truth table, and I'm asking you to compute the size of the smallest circuit such that every output bit of f is computed by some gate in the circuit. And it turns out that this is NP hard. If I give you a partial function as the list of pairs xf of x where f is defined, again, finding the size of the small circuit that agrees with f on all these pairs is also NP hard. And also if I give you a partial two-player function, then it's NP hard to approximate the communication complexity over so the deterministic communication complexity of f is NP hard. It's hard to approximate, in fact, up to a constant factor. And so these results kind of all fall in this meta complexity.
For the second, you mean a Boolean function?
Yes, sorry. Yes, the second is a partial Boolean function. So its output is actually
output or Boolean you need, or partial. Sorry, you cannot do it for standard Boolean function. You want them to be either partial or multi-output.
Right. Yes, indeed.
And
yes.
now the meta question. So now we have heard and forgotten probably all this history. So but can we now switch to an undergraduate mode from the conference mode? So you will explain the proof of some of these exciting results completely, or it's
yes.
still no hope?
Say again.
So maybe it's complicated proof, and we can only get some idea.
I'll prove the first thing completely. That's the main plan for the rest.
So we are now going. We should understand everything what you say, and not before you say about SDK. And we didn't ask what is SDK because it was conference mode. But right, now, if you say something, we should understand this.
Perfect.
Unless we are give up and accept we are stupid and can. Okay.
Okay. Let's do it. Yes, that's the plan. Great. So that was actually what I was planning to do, starting on the next slide. So, okay. So all right. So okay. So we're going to prove this. So I give you. So the problem is I give you a total multi-output Boolean function, and I ask you to compute the size of the smallest circuit, which such that for every output bit of the function, there should exist a gate in the circuit, which outputs that bit. Okay. All right. And we're going to prove that this is NP hard, and we're going to do it by a reduction from the R-bounded set cover problem. Okay, so in this problem, I give you as input a family of some sets, S1 up to SU, say. These are subset over the domain, so the domain is 1 to n, so all the numbers from 1 to n. And the family, the promise is that the family covers the entire domain, right? So the union of the sets is n, and that every set is actually not too large. It's bounded. It's actually size at most r, where r is in fact some constant. We'll see how r comes in. And what I'm asking you to tell me is, I'm asking you to tell me the smallest size of a subfamily that still covers the entire domain. Right? Mm-hmm. Yeah, so more people can turn the video on, by the way.
And it's NP complete in the standard sense, and it's kind of difficult result, or we should just read the simple proof and we'll skip now for simplicity.
No, so actually the result is not just it's NP complete, it's NP hard to approximate. And the
NP hard, and we need the hardness approximation.
Indeed we do, yeah. Yeah. So in 2001, Luca Trevisan has shown that if you take any constant alpha, this problem is NP hard to approximate up to, even with up to a factor approximation of alpha. Meaning, for every language in NP, there will exist some, I should have fixed this. So this R actually only depends on alpha, I believe. So, so for every alpha, there exists an R such that every language for every language in NP, and I can construct a map which maps an input to L to an instance for R-bounded set cover and a number K, right? And it'll have the property that if X is in L, then the cover size of this instance is at most K. And if X is not in L, then the cover size of this instance is at least alpha times K, right? So think of alpha as 5 or 10. So there will be some R, which is maybe 100 or something. And I have a family of sets S, and if X is in the language, then there will be a small cover. And if X is not a language, every cover will need at least 10 times as much, as many.
And so since it's a gap reduction, then it's probably use PCP, all these tools.
Yes, it uses PCP, indeed, yeah.
Yeah. So it's kind of deep result. And we will use it as a black box. We do not need to understand the proof.
That's right. We don't. Yeah. In fact, I haven't seen the proof, to be honest. I've seen some NP hardness approximation proofs, but not this one. Okay. All right, so our main theorem is a reduction. So it says that there is some random, and in fact, it's a randomized reduction. So there's some polynomial time computable map randomized in randomized polynomial time, which accepts as input an instance to the R-bounded set cover problem, and outputs a multi-output function f and the number k, such that if I compute the size of the smallest circuit for f and subtract k from that, that gives me some approximation of the cover size of this instance. Okay, so this number size of f minus k is upper bounded by the cover size, and it's at least 1/4 of the cover size. So it gives me a factor of 4 approximation to the cover size.
But since you have this k, you cannot say that approximating a size is hard. You just say that exact computing of size is hard.
Yes, exactly. That's where you lose. So you could say that maybe additively, there's some additive error that you can take in, but that's it. Yeah. So, okay. And what happens is that, you know, no matter which random choice you choose, this size of f is going to be at most k plus the cover size. And for most random choices, with high probability, the second condition happens. So the second condition doesn't happen always. Okay, so now let me make some drawing and to give you some, like, the basic idea for the reduction.
So you have a set and you want to get a cover, a small subcover, yes. And then somehow, depending on this, some function should be either simple or complicated. So if the cover exists, it's simple. Indeed. And if it doesn't exist, it's complicated. Okay, strange, but yes. Why not?
Yes, indeed, that's it, yeah. Right, so we're given this family, S1, S2, and all the guys in this family are small. Right? Their size at most R is some constant, like 100. And we want, what do we want? We want to construct, well, some function whose hardness, some multi-bit output function whose hardness approximates the cover size of this, right? So we want some function. So let me tell you how the construction, what's the idea behind the construction. I will start by constructing some Boolean function t. So t is a function. So t is a function which accepts as input some m bits, where m is something like log n, and outputs a single bit. So that's a Boolean function. Okay. And here's how I'm going to construct t. I'm going to take, let me make a drawing here, and this would be all the m-bit strings, okay? And t is some Boolean function, so it's you fill this space with zeros and ones. And what I'm going to do is I'm going to split this space into n parts. This would be part 1, this would be part 2, and so on.
But m is what? It's not related to n or u, or it's just some new parameter.
Let's take m to be like 3 log n. You can probably do a little better, but right. So the size of this thing is
n cubed.
Like n cubed. That means that each part, and these parts are just the same size, and they should be easy to compute with, you know, which part you're in. And so think of each part as having size like n squared, and you have n such parts. Okay. Now I can, for instance, define the following functions. I can define for each part ti. I can define for each part I can define the function ti, which is equal to the function t. Okay, and think of t as being chosen uniformly at random. So it's just a uniformly random function. And now I can define the functions which agree with t on a certain part, if x is in the part pi, and which are 0 elsewhere. Right, so for instance, t1 would be the function that is 1 here, but 0 elsewhere. No, it's not, I'm sorry, not the function that is 1 here. T1 is the function that agrees with t on this part, whatever t might be in here, which is it's uniformly random, so it's going to be some 0s and 1s, and it's 0 elsewhere. Okay.
So we take a random function t and then split it into a very simple predefined parts of a set of size n cube.
Yes, indeed.
Okay,
yes.
But why do we do this? What we try to achieve, or what is our main idea, or what is happening? What is this?
Yeah. I will say, sorry, it's a bit to swallow before I tell you the idea, but once you see the idea, you'll see that it's kind of a natural thing to do. Let me just give you one more definition before explaining the idea. So now I have this instance of set cover S1 SU, and I can also consider the function which equals, if I have one of these sets, right? These sets, some Sj chooses some of the parts, right? It chooses at most R of the parts from here. And I can define the function which agrees on these with T on these parts and is 0 elsewhere. So this equals T of X if X is in some part Pi and this part is in Sj and is 0 elsewhere.
So you have this individual parts of this random function, and then you group them into block parts according to this Si. And you say that if there exists some cover, then something suddenly happens. And if there is no cover, then something doesn't happen suddenly.
Yes.
Okay, but what is the something and why it happens or not?
All right. Okay. So let me start by saying the following. So suppose that you have some cover of n. So what's a cover? Is you pick some of these guys, right? A few of them, and they should cover, when you take the union, they should cover all the n. So if you have a cover of, then you can obtain the entire function t by doing an OR for j. If you have a cover, some cover, right? Then this holds, meaning that I mean, all these SJs, if the union of these SJs covers everything, so every part in the domain is included in some of these SJs because I have a cover, right? So if I take the OR of this, eventually every part will be equal to T. Right, so let's do this very slowly.
Yeah, but this will create a simple circuit as if you had TCJ as an oracle.
Yes,
but they are random things, and how can you?
TCJ has maybe it's just simple.
No, but T was random.
Right, but yeah, so
but
the idea
has just small support or something like that.
Right, indeed, that's it. That's exactly the idea. So
so I didn't get what Sasha said, but okay.
I mean, so these sets T as J just have small support, you know, compared to all.
No, but all PPs are of the same size n square. So as J is several n squares. So why it's so simple? It's just
no. This guy is not simple. So the only thing that this says.
Yeah.
So what if okay.
Okay.
So
let's continue. Maybe I'll see what is happening.
Yeah. Let's continue. But you're on the right track. So you could make a conjecture like this, right? So conjecture, which is exactly what you said, is that if we are given you know, TS1 up to TSU for free, whatever that means.
Yeah.
Then the conjecture would say that the best thing that we can do, so this would give you a circuit, right? So if I give you TSJ for free, I give you gates that output to the TSJs.
Yeah.
One thing that you can do is take a cover and do the OR of these gates, right?
Yeah.
And then you could conjecture, and it's reasonable to conjecture that this is actually optimal, that this is the best that you can do. Then the smallest circuit, the smallest, the best you can do, let's just be vague. The best you can do is the above, right? Is to take an OR of the covers.
Yeah, so since our oracles compute complicated functions, we cannot hope to do something without the oracles. So we need the oracles to cover all the set. And so the minimal number of these oracles is more or less the minimal cover.
Right. And intuitively, that's what's happening, right? So yeah. You could make this conjecture precise in the following way. You could conjecture that the cover size, the cover number of this family actually equals, or at least approximately equals, the size of the smallest circuit which outputs T and all the TS's minus the size of the smallest circuit that only outputs the TS's. This would be something like a chain rule. Right, that's a way of making the conjecture precise. Right, so how many more gates do I need in order to compute T compared with the number of gates, in order to compute T and all the TSIs, all the TSJs? So how many more gates do I need in order to compute T and all the TSJs compared with the number of gates that I need to compute only the TSJs?
You mean?
No, what? Okay.
So you mean that in one direction this is trivial or what?
Yes, indeed. In one direction it's trivial. It's trivial to show that this is at most, right? Or in other words, if I want to compute T and all the TSJs, I only need a circuit that I can take any circuit that computes all the TSJs and I add this OR to it.
Which requires cover -1 ORs. You don't, or you assume you allow multiple inputs. Fan-in is what?
No, let's say that the fan-in is binary, actually.
Binary, yeah. Binary. Then it's more or less cover -1 maybe or more.
Yes. If you want multiple fan-in,
this looks okay, but now it seems that you are cheating because, of course, if you use, but before if you use simple circuits in Oracle, you can use it or not use them. And now you need to when this in the size in the right part size of TS1, a minimal circuit is a circuit. And you can take something from inside and then use it and
yes.
So
it's not clear all this conjecture is true because it could be that for TS1 up to TSU, in order to compute all of those, like maybe the best thing to do computes T along the way, and then it would just be 0, this value, right? I mean, it could be that the best way to compute TS1 up to TSU would be to first compute T, or I don't know, something like that, and then check if you're, I don't know, something like this. You compute T, you check if X is in T, and then if X is in part SI.
Yeah, right? And you need only, since this R is rather small, since the side of the cover is just a constant.
No, the size of the cover is not a constant.
Not a constant, but it's logarithmic. So
it's logarithmic in the size, indeed. Yeah. Mm-hmm.
Yeah. So you need very kind of very precise.
No, sorry, it's not logarithmic in the size. So the size of the cover is going to be roughly n. It's n by r or something, right?
Yeah.
But the input is 3 log n, right? So the total size of the function is at most n cubed. So it's polynomial, so these things are within a pool.
Yeah, so you have n cube n cube values and about n things. Yeah. Okay, but still what is the typical size of the right hand thing? It's more or less like n cube or something like this.
The right hand thing, yeah.
Just size of t, normal size of t is,
yes.
is like an n cube or something like this.
Yes,
and here in the left hand side we have something smaller than u, which is how it's related with n.
Right. It doesn't seem that it's not clear that why this conjecture would be true. It might simply be false.
And what is the approximate order of magnitude of u? So u is how u is compared to n.
I think it's order n, but I don't remember. But I think it's order n.
Mm-hmm.
But still, that wouldn't help you, right? I mean,
yeah. Still, you have more or less like n in the left hand side and cube in both terms in the right hand side.
Right. I mean, you could say. I mean, these terms are comparable. Why and this exactly? So you're right. Just the size of TS1 up to TSU, you'd expect it to be something like n cubed. But the cover on the left is at most n, right? Because any cover size would be at most n.
Yeah.
So why would you expect they to be so finely close that you could actually just extract the? I mean,
yeah.
Maybe it's true for a random function, but even then you're like, why would it be true? Because maybe it's just not true. And kind of I think that kind of the really bright idea of the proof is, which wasn't mine, so I can say that, is to have some control over this. Like, because, you know, this kind of statement, it's really very rare that we can do this in complexity theory where, you know, you can argue something that the best thing that the circuit can do, the best thing that an algorithm can do is to behave in this way. That would be like that's the holy grail of complexity theory, that we could argue like that. We have no idea how the algorithms are working, right? We can't say something like that. So what's the hope to prove this conjecture, even if it's true? None. But there's a trick. And this trick is actually it's a very cute trick. So when can we say something about how a circuit works? Suppose that, so I cannot say, if I ask you, right, let me make it. If I ask you, what's the best circuit for this TSI, right? What is that? All you can say is, I have no idea, right? Because I can't say anything about how this TSI is computed. But what if instead of asking you to compute not just TSI, I ask you to compute more? And here's the idea. So if I have a function f, right, the Kenny Boolean function, then DNF of f is the multi-output function which on input x outputs every gate in the canonical DNF for f, right? So I have some function f, and out of this function, I can consider the canonical DNF. I'm also going to call it like this. The canonical DNF for f is just the OR, and I have a branch for every x in f that f maps to 1, right? And then I have some gadget here which checks if the input z equals x, right? So let's say that the input is z. Right,
so instead of computing one function, you can compute a multi-output function, which is, let's try to understand this better. Try to compute what? So it computes for every.
So look at this circuit. So take f. You see, you understand what's the canonical DNF? What I mean by the canonical DNF for f.
Yeah.
It's the circuit which has a big OR. It has a tree of ORs, right? And each leaf in this tree of ORs corresponds to a one input of the function.
Yeah.
And then I have an AND, I have some gadget which has a bunch of ANDs and a bunch of qualities, and it checks whether the input. So it checks whether the input is one of these guys. Right. That's the
canonical DNF. Yeah. But you want to, so you, except for f, you want to compute whether the input equals this point, and for all the points where f is 1.
Yes, but there's a circuit that does that has exactly this behavior.
No, so also you want to compute the intermediate OR gates here, yeah?
Everything. So Yeah, so take this, so give me a sec. So take this circuit that behaves like this. I just made a drawing of the circuit. It's this guy, right? This circuit has a bunch of gates, right? Now think of the multi-bit output function, which on some input Z outputs, or I did some input X here, so I switched the Z and the X here. So let me just switch it back, right? So, it's a circuit which on input X should output every single gate, every single bit which is output by any gate of this canonical DNF circuit.
But what I don't understand, so the canonical circuit is not canonical because you can compute all in different orderings.
Yes, yes.
So you fix some ordering or what?
Yeah, you fix a specific way of implementing. Yeah, so I guess it's not canonically, right?
You not just compute all the bottom gates and on the top gate. You somehow ask for compute every input in one specific. So you choose some specific order of making ORs, and you want to compute all this ORs in this.
Indeed. You fix some way of taking a function f and writing down this DNF-like circuit for f, right? Mm-hmm. And this DNF-like circuit for f has some number of gates. Let's call that number k.
Yeah.
Then this DNF of f is the function which on input x must output all the k bits where each bit corresponds to one gate in the circuit, is the output of one gate of this circuit. Right? If the circuit has k gates, then I should output k bits, and each bit is the output of one of these gates.
Okay.
Okay. So here's a claim that the size of the DNF the size of the small circuit that computes this DNF is actually just k. Right? That's my claim.
Size of DNF is?
Right, so this DNF of f is the multi-bit output function, which on input x must output every single bit that appears in, every single gate that appears in the circuit.
And also the gates which are not shown, which are needed to compute the end in this Z is equal to something.
Indeed. This gadget is not a black box. It has some ands and some ors.
And these are also inside this things.
Yes, and these are also required to be outputs of this function DNF of f.
Yeah.
So for every AND gate, for every OR gate, for every negation gate in the circuit, I add one, and the total is k. So k is really the number of gates in this. I call it canonical, but it's in this DNF-like circuit for f. Right. So and my claim is that
So you are saying that you have some function DNF of f with k inputs, and its size is k.
No.
Input to the k
inputs. No. Inputs is m.
No. Sorry, outputs. How many outputs are in DNF of f? K.
Right.
So, yes. And you're saying that the size is k.
Yes, and I'm claiming that what I'm claiming is that if I ask you to compute every intermediate gate in this circuit, the best thing you can do is actually to use this circuit. You cannot use any other circuit.
But it's like you're saying that the function with k outputs has complexity k. It's like you cannot have less than k.
Yes, indeed, that's what I'm saying.
But imagine,
which is I guess obvious.
But imagine. So you say that, for example, in this small rectangular boxes, you compute some ends, like where you check whether x is equal to something, and then you compute some ends, and you compute the same ends in different things.
Indeed.
And sorry. Then you can do something and that.
Indeed. Sorry. So k is the number of unique gates in the circuit. You're right.
Unique outputs, you mean?
Unique outputs, indeed. So I will plug in this circuit in such a way that I have no redundancy. Actually, you're right. So and that's necessary to argue like that, right? So if at some point there was a gate which was already computed by some other gate here, I'll just take these two gates to be the same, and since I have multiple fan out, I have no bound on the fan out, so I can just take them to be the same gate. right?
No, things become more and more strange. So let me, since we are in undergraduate mode, I would like to ask, for example, Sasha, do you understand what is happening, or not?
So I do not understand. So this claim, size of DNF of F equals K. Does it require some proof, or is it obvious?
So it's
if
obvious
it's obvious,
once you
then
understand.
I am fine.
It's
if
obvious
it's
once. No, it's obvious once you understand what I'm saying.
Okay.
Once you understand what this function is, DNF of F, the claim is obvious.
No. I'm just want to understand. So this is some function with K outputs. So we are saying that we can compute it somehow by a circuit of size K, and of course we cannot have a circuit smaller.
Not of course, but because we assume that there are no
repeated
wires which have the same thing.
Yes.
Because if we have these wires, we just delete it from the circuit.
Yes.
So we start with the canonical. We start with some circuit which computes F.
Right.
And the circuit of a special form is just a long OR of small blocks which check equality.
Yes.
Now in this circuit, some gates, some wires can, by chance, have the same value.
Sorry, before you explaining that, I guess I'm not understanding why you're explaining that. Maybe you mean that in the definition of the size for multi-valued functions, we can have the same gate for two different outputs, or what?
Yeah, we can have the same gate for two different outputs, yeah.
But if we do not allow this, then this claim is so then it's obvious, right?
No, but different notion of size. But okay, but still,
okay, yeah.
So how I understand what is happening. So we take this circuit, and then we delete all the wires which are.
Sorry, you're explaining how is DNF of F is defined, or what?
How F is defined. DNF of F is defined. So we start with a circuit for F, then we delete whatever repeats other parts, and then all the variables we declare now as outputs.
You mean you're merging any two gates which compute the same function?
Not merge, I just delete the gate if it computes something which is already computed by the earlier.
Okay.
Yeah, you can think of it as merging, but yeah, fine, yeah.
I delete, because it was a tree, so I also delete everything which was necessary to compute this.
Okay.
So
then
part of the tree.
You take this reduced DNF of F and you want to compute on for every X, what is the value of the gate for every gate? What is the value?
For every line of the program, we want to include this line. We declare it output.
Okay.
Yes. And so since all lines compute different functions, because we deleted the lines which compute the same function, then by definition we cannot share anything. So we need to have this K.
Right.
Yeah.
So now it seems clear.
Now it's clear.
Okay, Lyosha, is it clear or not?
For me, it's clear.
No, okay, that's good. But I don't know. The point is, do I understand what is happening or not?
Понял.
Okay. So okay, let's try to. It looks like a complete cheating, but okay.
Yes, it is actually. Yes, I agree.
No, but who is to be cheated? that's what is.
Yeah, but that's actually this. So this gives you like control over, like, remember when I was saying that, well, we can never say that a circuit is going to do this, that it's going to compute the function in this way. It's very rare to actually. Rosen-McKenzie result does exactly that, but these results are very rare in complexity, right? So what hope did we have to prove this, right? That was kind of what I was saying earlier. But now it turns out that if I require that in addition to computing the T of SIs, I require to compute all the gates in the DNF of T of SIs, suddenly I can control how the circuit is behaving. I can prove this. Mm-hmm. If I have any circuit which simultaneously computes the DNF, all the gates in this DNF circuit of F1, all the gates in the DS, etc., then for every unique gate appearing in these canonical DNFs, I call it canonical DNFs, but it's maybe a terrible name. For every unique gate that appears here, there will exist. That gate will appear in this circuit. I mean, there's no way of avoiding it. There's no way of avoiding this gate.
No, but this I don't understand. So imagine you have these canonical circuits, not canonical, but chosen circuits for F1, Fu. Mm-hmm. And of course, they refer to disjoint part of the input space.
No, they don't. No. This
okay, okay. They can even they do the same. But then you have this rectangular box in one of them, which checks whether X is equal to some string. Yeah, mm-hmm. And then in different rectangular boxes for F1 and F2, and for example.
Yeah, you have the same rectangular box in F1.
You can check the same thing.
Right.
So when you want to compute not only one, so when you compute only one Fi, it was clear, not this Fi, but also this DNF of Fi, this all intermediate things. Of course, there was no way to economize because we need to have all of them as output.
Right.
But now, if you put DNF for F1 and Fu on side to side, then of course it can happen that some gates in different in DNF of F1 and DNF of F2 compute the same thing.
Right. It's definitely possible. Right. You're right. But what I'm claiming is that for every unique gate that appears, and by unique I mean unique everywhere. So look at all the functions
of the function it computes.
Yes, indeed. Yeah. So if you take a circuit, so any circuit that simultaneously computes this, now look at all the gates that appear in all these DNFs. All the gates that appears in all these DNFs, but merge together the gates that happen to be the same, right? And count how many unique gates that appear in the entire thing. It's not the sum of the number of unique gates that appear in each Fi.
Yeah, but then it's not what is the lemma. It's just if the functions are different, then
they have to be there. That's right. It's trivial lemma. Yeah. It's a trivial lemma. I'm just trying to Okay. Now.
Okay. So cheating becomes more and more extensive. Okay.
Yes, exactly. So now I'm cheating many times. Yes. But now I can make the following claim.
Yeah.
If I choose T at random, as above, as we said above, then with high probability, the covered number is actually equal up to a factor of 4 to this value. It's the difference. It's how many more gates I need to compute T and all these DNFs compared to only needing to compute these DNFs.
So in the right-hand side, the size also involves all the economies which come out of the coinciding functions. Yeah.
It also involves what?
No, if there are equal things in DNF of TS1 and TS2 and so on, they are economized somehow both in the left term and the right term.
Yes. Yes, this size is the size of the smallest circuit that computes all of these simultaneously. And we can see that doing so is, you basically take, so this is basically the number of unique gates that appear. It's this number that I was trying to refer to in this lemma.
Yeah.
It's the number of unique gates that appear in all of these DNF circuits.
So what you essentially say, so okay, what you anyway, let's consider the circuit for the right-hand side. This cannot minimal circuit for the right part.
We can draw it actually. Yeah, that's right.
Yeah. So, and then what you say, that the simplest way to add some new gates to compute T would be to use only the output of the circuits and only in the OR way, so to say. So actually, normally you can think that there are some intermediate wires in the circuits for TS1, TSU, which are somehow better for computing T.
That could happen, yeah. But only up to a factor of 4, I claim.
Up to a factor of 4, this things doesn't change the complexity.
Yes.
That's what you're saying.
Yes, indeed. Right. So there's one direction that is easy, right? So this is at most, this difference is at most the cover size, because I can use the OR, right?
Yeah. Even
what
minus 1. But
minus 1, I guess.
Yeah, but the non-obvious part is that it's just for random T.
For random T, this is going to be at least the cover size over 4. Roughly. Yeah, maybe there's some plus or minus.
Yeah. So for random T, you cannot do significantly better by using some intermediate gates of functions TS1,
yes.
TSU. So that's what is now needed to be proven.
Yes.
Yeah.
Okay.
So what now again the question? So is it understandable fashion? Is it clear what Bruno is saying or not?
It's not clear what you are saying, and everything else is clear.
Okay, yeah. That's perfectly fine. And Bruno, what?
I forgot. The function TSI. It's more or less clear. I forgot some things. The functions TS, the parts PI in your partition of 0, 1 to the power m, they're chosen in some simple fixed way, or they're also chosen randomly?
No, they're chosen in some simple fixed way.
Okay.
So
the randomness is over the choice of T. Yeah.
The randomness is over the choice of T, indeed. These parts are fixed, yeah.
But the fixed part, somehow, the way they are fixed is not used or referred to in this argument up to now. So now, just for anyway, even there are complicated parts, still this difference is at most cover.
That's right. I think actually the only thing you're going to use is that they're roughly the same size, or they're
So even later we won't use that they are simple. We just use that they are of sizes.
I guess that's true. Yeah. Yes. But we'll check. Let's do the proof. So okay. So now I have to prove this chain rule. Right?
Yeah. I also want to see the statement again. So K, there was some K, if I remember. There was size F minus K should be smaller. The original theorem, because now we understand much better. I forgot the original theorem, the two things we need to show.
Do you mean this?
Yeah. So K will be the size of T of the covers.
Yes, so exactly. So this K is going to be, so what's this F? This F is T together with all these DNFs. And this K is just the size of the DNFs.
Yeah. So the size which we subtract this of TS1, TSU is not something which is difficult to find, because we start with the optimal circuit and with some circuit and just make it optimal by requiring all wires to be in outputs and deleting the identical wires. So the right size is easy to compute.
Right, you can compute it deterministically.
The computation of the left-hand size is a hard problem because it helps us to distinguish between large cover and small cover.
Yes.
Okay, so Bruno, is it okay or not?
For me, all is okay.
Okay.
Cool. Скажи что-нибудь.
Все я понял.
Okay, he understands also.
Okay, cool. All right. So okay. So let's do that. So
maybe somebody else wants to ask a question. Let's still. I ask some people who are. I know.
Слушай, Саш, погоди, что у тебя там с микрофоном? Все время какие-то помехи, когда ты говоришь.
Okay. Let me try to. А сейчас лучше?
Да, только тише.
Yeah, it somehow automatically increases I make the sound.
Нет, погоди, тебя совсем не слышно.
Now you cannot hear me.
No, we can't hear you.
Hello.
You're very silent now.
And hello.
Now it's better, yeah.
Better.
Сейчас хорошо.
Окей. Ладно, пусть так будет.
О, отлично.
Yeah. No, maybe I should just be less excited and the microphone will be better. Okay, so there is no question. Other people don't want to ask questions because since we are in the undergraduate mood, everybody should understand, has the right to understand what is happening.
Right. But feel free, yeah.
Okay.
Okay. Right. So let's prove this. So let's prove that with high probability over the choice of t, right? This thing is large. And here's what we're going to do. We're going to show that if we have a choice of t such that this is false, then t will have a short description, and so it can't be random. Okay. So let's assume that. So let's assume that if the number of gates that I need to compute t in addition to the number of gates that I need to compute these DNFs, if that is less than the covered number of SI over 4, then let's show that t has a short description. So it can't be random.
Yeah.
So let's find a way of describing these guys, which is
short description given the S's.
No, just a short description. It's called
even stronger because.
And so you will say now that the description is just consists of pointing out what are the additional circuits, additional gates, and what inputs they are using.
Yes. Yeah, exactly. So
just the simple bound you claim should be enough to prove that. Yeah.
Right. Yes, that's it. That's how we do it. So suppose that I have a circuit which computes T and all these DNFs of these TSIs, and the number of gates that I need to use is at most K plus, let me remember. And the number of gates that I okay, so I don't see my notes, so I'm going to try to play by ear. So, and the number of gates that I need is at most K plus some value, which I will call L. But simultaneously, the cover size of SI is at least, let's say, 4L. Okay? So the cover size, well, in fact, let's say that it equals 4L. Because I think I need it on the directions. So the cover size of this family is 4L, but I can compute T and all these DNFs in fewer than K plus L gates, where K is the number of gates that I need to compute just the DNFs.
To be pedantic, you should say that cover is not always divisible by 4. So it's not exactly 4.
Yes, indeed. And here you get maybe minus 3 here or something.
Yeah,
I mean, there will be something that appears here, but let's say it's
okay.
Okay. So what does this mean? So this means that I have some circuit, right, which computes one of the gates outputs T, right, and it has K plus L gates, but somewhere in the middle here, I also can compute all the DNFs. Now, if I look at the lemma that I have here, it says that this circuit must have a single gate for each unique gate appearing in the DNFs, right? So K out of these gates in this circuit, we already know what they do. So K out of the gates in this circuit are the gates that compute all these DNFs. There's just no way around that, right? So I have K, and then I have maybe L extra gates. L extra gates. So that means that I can write T of X as some sub-circuit, right, C, which has input maybe X, so because you could feed in X in here, but also the gates G1 up to, and also some let's say,
gates taken from the previous circuit.
Gates taken from the previous circuit, and I think I'm just going to do 2L. Of course, you can do better, but because if you have L gates, I'm just roughly upper bounding. If you have L gates, the Fn is 2, so certainly fewer than 2 L gates. Of course, these gates have to feed into each other and so on. But, so it's actually maybe L plus 1 there. But as a rough estimate, this is true. So if I have this thing, if computing T in the DNFs is at most K plus L, then I have some circuit C, and the number of gates in this circuit is at most L, right? And this circuit takes as input the input X, and some of the gates that appear elsewhere in this large circuit, and it outputs T of X, right?
Yeah.
Okay. So now here's what we're going to do. Okay, so each GI is a gate.
Sorry, it's not sorry. So you just take a circuit which consists of this L extra gates.
Right.
So
Yeah.
we just leave the lines which computes this extra lines, and these lines use some standard lines, and at most 12 of them. And so we just write this.
Right. Because this subcircuit actually has size at most L, and you can only feed into it at most, let's say, 2L gates of the
Where comes 2L from?
Yeah, it's a stupid way of counting. You have L gates, the Fn is 2, so it's 2L. You could actually argue that because it's a tree, you could do a little better.
It's not necessary. Yeah.
Or yeah. So
L plus 1, yeah, but
L plus 1, yeah, but let's say 2L because I'm lazy. So maybe you can improve this 4 to 3. Okay, so now each of these GIs is a gate in some DNF, in one of these DNF of some SJ, right?
Yeah.
Yeah. So if I let's assume, let's say without loss of generality, just that G1 just for simplicity, that G1 is a gate from the DNF of S1, and G2 is a gate from the DNF of S2, and so on. Okay, so GJ is a gate from the DNF of SJ. I can always reorder the S's and maybe copy them in order to make it like that.
And so now you say that each gate, each JI is taken from some SI, and there are only 2L of them, while minimal cover is 4L. So there should be some part which doesn't depend on the some part of our division, which is has no influence on this G1.
Exactly. Yes. Exactly. So if you look at your parts, right? P1, P2, P2, and so on, P3. And here's what we're going to argue: is we're going to argue that since the cover is SL, sorry, since the cover is 4L, but I'm only choosing 2L parts, these parts can, sorry, I'm only choosing 2L sets, Sj. These sets Sj will actually only cover a few of the parts. So it will turn out that, you know, if I take S1 union S2 union, etc., union S2L, the number of parts that I can cover will show is at most some small fraction of the parts. I think this is it, if I remember correctly. Right, so yeah.
No, I don't understand. Why? You know that there exists no cover of size 2L.
There exists no cover of size better than 4L. You need 4L to cover everything. Yeah, but I'm going to claim that if you only have, if you only have 2L, then it's not just that you can't cover everything. You're actually missing some 1/2R fraction of all the parts.
No, you divided the set in all pieces. So one of the you want to say that one of the pieces is not covered, or something
more than one. In fact, the fraction of 1/2R of the pieces are not covered by these S2Ls.
R is what? I forgot.
R is the size of the set.
Right.
Here we use that our sets are small.
Right. Here we use that our sets are small. Yeah, in fact, R is something like 100, say, some constant.
And so why can somebody explain me why the small sets fail? Here I am lost. So
to prove this,
yeah.
This inequality follows because S is small. The size of S is at most R.
Yeah. So why? So imagine that we can cover not the entire thing, but by 2L. But then you say that somehow by 4L we can cover everything.
Right. Right.
Why?
So, okay. So this should be clear, right? The size of S1 union SL, S2L. This is at most n minus 2L, right? This should be true. Right? This should be easy to see, right? Because I need 4L S's to cover the entire thing, right?
Oh,
I need
if you can cover each single non-covered element by one set, you will just have 2L additional parts.
Yes, indeed. That's it, right? So
okay, n minus 2L.
And I can always do that, right? Because the S's cover the entire domain.
Yeah, and then
the L is big.
Yes, the L is big, right? Because
you can cover with 4L.
Set, right? So 4L, each set can only cover R guys. So 4L is at most n by R. Because each set is small, right? So in order to cover the entire thing, I need at least n by R sets.
Mm-hmm. Yeah.
Right, for L. So that means that this thing is at most n minus n over 2R, which is what I claimed.
Mm-hmm. Yeah. Okay.
Okay, so that means that if I have these 2L sets, the number of parts, I'm missing like a constant fraction of the parts, right? I'm missing a 1/2R fraction of the parts.
Yeah.
In my cover. That means that...
the strange thing here is that we use both the lower and the upper bound for the cover. In one place we use that the cover is at least 4L, and in another place of the proof we are using it at most 4L. Right?
Yes.
Why not?
Yes.
So say it again, where we use what?
So just now we have used that the cover has at most 4L sets to prove the last bound, right?
Yes.
And before we use that, we need at least 4L sets to show that S1 union S2L is at most n minus 2L, right?
Yes,
Which
so
I imagined that we will be using only the lower bound for the cover.
Yes, but I mentioned
but
this
it's
too,
not
actually.
the case.
You saw that even when I wrote it, I just said, and this is small. But then I remembered, no, you need both directions. So it's also a bit like why, but I don't really. I mean, of course,
okay.
Yeah. So it's
okay. Somehow I'm confused, but let's continue. Maybe later.
I'm also confused. So at least two people. So for the two equations in blue and bottom, I still well the first one n minus 2l I understand, but then the one below, I have also trouble.
So for L is this cover size, right?
So Bruno, for the last equation, inequality, we need that the inequality n is greater than 4 times LR, right? For the last one.
That L is bigger than 4.
That n is bigger than 4 times L times R, right?
Yeah, this I understand.
And why is this?
Yes.
And why is this? Because we can cover n elements by 4L sets of size at most R.
Yeah, this is clear. And then at the right, n minus n over 2R. It's by substituting. Oh, it's easy. Okay.
Right.
Okay.
All right. Okay. So, but now we're ready to kind of give the short description of T. Right. Let's do that. So, so how can we describe T? We basically need to describe this part, these guys, right? We need to describe all the parts of T that are contained in any of these S's. And the number of bits that I need to do this is just this times n let me see, n squared, I guess, because each part has size.
No, we need to describe that are not contained. And the ones which are, so we want to describe the rest, the bits outside this cover of size 2L, yeah, I guess. And there is at least n divided by 2L, no? That's what you say.
No. I want, because, so T is obtained out of some gates that appear in the DNFs of SJs, right?
Yeah.
So I can describe T if I tell you what the circuit is.
Yeah, sorry, yeah.
So what's going to be my description of T? I tell you what the circuit is. The circuit is not large. The size of the circuit in terms of bits is something like L log L or something, right? It's a small circuit. And then I have to tell you which gates appear, right? So to tell you the gates, I can just put to tell each gate, I tell you what the SJ is for the gate GJ, and I give you a pointer to the gate in the DNF circuit of which I mean, right? I give you, so if you know SJ, it's easy for me to tell you GJ, that's just a pointer. So in total, all these pointers would cost you like 2L log of the size of the DNF. So it's something roughly, it's order L log n, order L log n. The thing that costs me the most is to specify what the S's are. But here's what I can do. I just tell you for every part that is covered by these S's, I just tell you the part. And that costs me n times 1 minus 1 over 2r times n squared. This is kind of the dominating term, right? Which is like n cubed minus n cubed over 2r.
You're saying that not the number of parts is at most n, but the union, the size of the R. Okay, sorry, yeah.
Yeah, indeed. The union of all these parts has size at most.
I mean, yeah. So elements of these sets are parts. Yeah. I mean, yeah. Okay.
Elements of these sets are parts. Yeah.
So you specify one bit for each part which is used, or you specify the number of the part.
So for each part that is used, I have to say what's the value of T inside this part. And that's like n squared bits. That's n squared bits, right? Each part is a subset of 0, 1 to the m, which has n squared inputs.
not inputs, but so for each part, you should say which gate inside this DNF for this part is used. Yeah,
it's log n bits.
Wait, which part? What do you mean part? No, wait. No, for each set S, a set S is not a part. I'm calling it a set, right? For each set S, okay, so let's see where we are. So do we agree that if I can I tell you what the circuit is, and if I can tell you what the SJs are that are fed into this circuit, just by adding some pointers, I can tell you what the GJs are.
Yeah.
Right. So this is not a lot of space. If I tell you what the S's are, just telling the circuit and these pointers is not a lot, right?
Слушайте, дайте я вам объясню. Я, кажется, понял.
So, but quite a thing that his Russian explanation will be more clear. But then you cannot check it. Okay.
Okay, I can explain it even in English, I think. So the random function is described by n cubed bits, right?
Yeah.
He wants to, Bruno wants to explain that actually under our assumption, it can be described in 99% of n cubed.
Yes.
And why is this?
No, you speak about the entire random function, all the parts of random function.
The entire T. T is defined on the universe of size n cubed, right? So we need n cubed bits.
Oh,
right?
Yeah. So, no, I was under the impression that you are saying that there is a part of size n over 2r, which is now completely random and is not related, the G1, G2L doesn't help. And only the circuit should determine it. But you want to speak in terms of the entire function.
Right. I want to say that the entire function has a description which is much shorter than n cubed bits.
So we will define the value of T on the union of all parts corresponding to sets SIs. I mean, those two times L sets.
Yeah.
And in total, they have 99% of the n cubed.
Yes.
But it remains to explain that we also need some additional information, actually.
Right.
Yeah.
And what is that information?
Right. So once you
what is the circuit C and how it's attached to the DNFs, which compute this SI things.
Yes. And the sets S and how the sets S are formed, right? So if I tell you the value of T on all the parts, I then can tell you all the SJs by saying which parts belong to each SJ. But that's very little. That's much less than S, right? That's like R log N or something bits. And now you know all the SJs, and once you know all the SJs, you also know what the DNFs of the SJs are. So by telling you pointers to these DNFs of SJs, I can tell you which gates you need to feed into the circuit. Kind of everything is small except for this, which is 99% of n cubed.
But if it were not the 99% of n cube, and if it was just n cube minus one part minus n, it would be not enough.
That would not be enough. That's right.
Because you need. So, can you say more details how much additional bits you need to describe the behavior of the missing
Yeah,
part?
I think it's going to be order n log n. I think that's it. Let me see.
And how can you get this? Why do you get this n log n?
So let's see. So suppose that I tell you all the P's, right? I tell you all the parts that are covered by any of these S's.
How much does it cost? You're telling the value of T in these parts.
Yes, I'm telling the value of T inside these parts. Yes.
Yeah.
That's 99% of n cubed. Okay, so I have.
Yeah.
Okay, so now I'm going to do it in little of n cubed, and I think I can do it in n log n. How do I specify now an SJ? What SJ is? I basically have to tell you which parts you glue together to make SJ. I have to tell you the set SJ. I have to tell you what that set is, right? So a single Sj can be described using R times log n bits, right?
Mhm.
A single Sj costs R log n bits.
Single gate in SJ or
No, we haven't arrived at the gates yet. I'm just describing Sj itself. What Sj is, what the Boolean function Sj, what is it? That's what I'm telling you.
Yeah.
And I'm claiming that if you already know the parts, I can just specify Sj by saying which parts belong to Sj. So I can just say the set Sj, and you know what, so this should be T. And now you know what T of Sj is, right?
Yeah.
So each Sj costs me R log n bits to specify.
Yeah.
I just say which parts belong to Sj. And there's the size of Sj is at most R, so
Yeah.
that's R log n bits.
Okay. But you have many of SJs.
How many do I have? I have 12 of them. Right?
Mm-hmm.
So this entire thing, to specify all the SJs, I have to use n log n, order n log n, because R is a constant, right? So, and L is at most n.
Yeah.
So now I've specified all the SJs, and that cost me n log n bits. Now that you know the SJs and you know the parts, you now understand, now you know what the T of SJs are, and because you know what
you should specify the wire.
And then you should specify the wire, exactly. So
Yeah.
now specifying each wire, so the DNF T of SJ, how large is, how many gates does it have? It has at most n squared gates, say, right?
Yeah.
Or n cubed maybe gates. So each TSJ has at most n cubed gates.
Yeah. So we have log n times
2L again.
2L again, yeah.
Which is again n log n.
N log n.
Okay, and
Yeah,
now you know which
so,
GJs. Yeah. And then the circuit
so
is also n
what
log n.
you say is not enough to have one thing uncovered but you don't need the linear bound, but you still need that most of them are, there's a significant number of them are uncovered.
Yeah. The linear bounds.
But if there is such a big gap between n log n that we have and n cube that we need,
right,
and con O of n cube that we need, why do we need such a large set like n cube?
We don't. I was just lazy to do the exact. I guess if you want to be very precise, you need you need each part to have k n log n elements where k is some sufficiently large constant, which is going to beat all these things.
For example, if you take just n square instead of n cube,
that's enough.
Perfectly okay.
Perfectly fine. Yes.
Yes, nothing will become more complicated or more.
Nothing, not at all. Sorry. Yes, no.
Yeah,
I was just overshooting. And, yes.
Okay, it looks.
But
like
also, you take R constant, but you can take R smaller a little bit, and then maybe you can use a weaker hardness result.
Right. So So in order to get some constant, we do need four factor of approximation hardness, and for that you need R to be some number, some constant. I don't know what the number is.
Okay. So R must be a constant.
Yeah, R depends on the factor of approximation.
Oh yes. Okay. Sorry.
No, that's,
yeah. So
I don't understand why it should be a constant. But okay.
No, that's not easy.
Why R should be constant in this argument?
Yeah, so it seems that we have some reserve here, some gap.
Mm-hmm.
So why cannot we use just a problem for a bigger R will be more difficult problem.
You're right.
Hard. So maybe what Bruno says, Bauwens says that maybe for this bigger R, the hardness result could be easier.
Oh, you're right.
But you even probably can take R to be like n, so the set can be arbitrary, and then there will be at least n squared.
No, n you can't do, but n you can't do, right? Because this n square, this n square shows up whatever you do, right? So.
Okay, but no, just look, n, there's n cube minus n cube divided by 2r. If r is n, then it's just n squared. So we save n squared, and we additionally have n log n, so n squared kills n log n. Right?
Right. Wait.
Yeah, but maybe there will be some problem with like with these arguments for L is at least n over 4, because there will be some rounding or something like this.
Yeah, so I guess the best that you could do, you're right, but I guess you're right. So it's enough, if the parts are big enough, it's enough that there's one part left, right? I mean, if each part has like n squared bits, say, then it's enough to have just one part that you didn't cover.
Yeah.
And I guess that you don't really need the hardness of approximation then. All you need is that there's a part that you didn't cover.
But there is a gap, two gap where you're coming from like L gates to L gates.
No, hardness approximation is not about how much part you do not cover, and it's how much.
Oh, I see. Right. You're right.
Yeah.
I see.
Yeah.
Yeah, that's right.
No, but if you don't use, if you have one uncovered part, then it can be always covered by one set.
Right, but in order to get these uncovered parts, you need this 2L, I guess. You're using this 4 here. Right, so Sasha...
Now what we are discussing is probably not whether you can improve your result, but when you can weaken to get simple hardness result, which since we missed this PCP argument,
right,
it would be nice to get it as simple as possible.
Nicer, I agree, yeah.
So for that, we just need that S1, S2L do not cover all the parts, or what?
Right, that would be enough.
Because
but the thing is that...
but they do not cover just because the size of cover is, the smallest cover is 4L.
Right.
That's it.
You're right, yeah, it does seem that way.
No, so what is the verdict?
Wait,
so we still need the 4 times gap in the cover size.
That's right, yeah.
But what we don't need exact, to the set to be that small. That's what you are saying. And this is unclear whether allowing larger set could help us for making a simple gap reduction.
I see. So you do need a gap, but you're saying, but you don't need, you don't actually need S to be small.
R to be small.
You need R to be small. No, but if you have the gap, then, well, R, so it would be enough if you had 1 here, right? So if you had 1, that means that you save on one part, at least. But then that means that n by r needs to be at least 1. At least 1 or not? No, sorry, 2. You need to have 2 here. 2 here. 2 here. That means, right, if you do need to have 2 here for the argument to hold. N by r should be at least 2. N by r should be at least 2. Which means that r should be at most n by 2. So you do need that the sets have size at most half of the n, which I guess you get even better, but constant is complete overkill. You're right. So maybe if you allow for something like this, you can get much easier hardness of approximation. That's interesting. That would make it.
But since we
nice.
don't know how the hardness is proven, we cannot say whether
Right, right.
or not.
That's
But
right.
where is the main? So where's the hardness of? So where we need approximation? So where we come from L to 4L somehow, right?
Right.
Yeah, because
Yes.
first we have more. We have this
And this
2L.
happens just in one place, right? Where we say that if we have L gates, then there are 2L inputs to these gates.
Okay, we have L plus 1 inputs if we are more careful.
Okay, so this is not. This will be maybe additive factor of approximation or something.
Oh, so if you say if we say that not 2L but L plus 1 inputs, maybe we can get much weaker.
But I don't. So there is. But.
So you could get L over there, right? That's true. And then, but you'd still need 2.
Okay, so if you have a circuit of size L, how many inputs can be in it?
L plus 1, I guess. Because
right.
if just every tree with L binary nodes should have L plus 1 leaves. It's not. There is no choice.
Okay, yeah, probably. So yeah, so probably we will need just the hardness of approximating up to like some additive factor like 10 or maybe even smaller.
Additive factor is something interesting.
Additive term. Sorry. Yeah. Okay.
yeah. Just.
Sorry.
kidding. Okay.
All right. So is that true? I'll think about it.
Okay, so I think we can now switch to maybe you should say something about the other parts. So now it's more or less clear, but that you can other statements.
Sorry, just to remind you, we actually should have stopped the seminar 20 minutes ago, but probably we can continue for some more time.
No, everybody can stop the seminar, effectively stop the seminar for him or herself, so it's no problem. And also we are too late for the seminar of the Moscow University, which is a shame that we cannot arrange them in different weeks, but okay.
I can say something about the other results. So the other results are actually very easy.
So it seems for me that you very essentially used the idea of the function is multi-output. Then you cheat by this by adding all the intermediate things. But now you have a partial Boolean function. How can you deal with this?
So the partial Boolean function result is actually a lot less interesting. When I first proved it, I had this very long proof using Cashman-Vigdison games. I thought I was being really smart, but it turned out that there's like a 3-line proof, which I don't remember right now, but it turns out that it's actually a very simple argument, turns out. But I'm afraid I'm not going to be able to recall it.
How can you, what is the advantage of having partial things? Why it does help? Or
so here's why it helps, because actually the list of pairs can be much smaller than 2 to the n. How was the easy proof like? It was so easy. It's like a cover.
So you say that you don't use the first result, you just give some completely different proof from
completely different proof. Yes.
Okay, then it can be postponed to your next talk if it's different proof.
Yes.
It would be interesting to hear this.
It's not, well, it's too easy.
It's even better. And about the third proof, what you can say?
Oh, the third proof is a simple reduction actually from chromatic number. I can draw the reduction in
No, but it's also not related to the first proof.
It's not. It's not. All of these proofs are different. But it turns out that you can use like if you have a graph and you want to know its chromatic number, you can construct a two-player partial function such that the number of leaves in a deterministic protocol actually approximates the chromatic number by a factor of 2 or something. So it's really, really very...
Okay, then maybe you can just not since we are now somehow in a hurry, but psychologically, maybe you can tell us a different time. But just I want to ask some philosophical question. So there is it seems there is a big problem to show that minimal circuit size is hard, and you are somehow in different ways. Your seem to be closed from different direction. What do you think that just a small additional trick is needed and you are done, or that all these things are much more simple than the one output?
So I am absolutely on the edge here. You know, there's like, for instance, okay, so we've proven that this multi-output function is hard to compute exactly. That's nothing. I mean, if you really want to prove circuit lower bounds and you want to use like this idea that there might be witnesses of hardness and so on, you're totally satisfied to have an approximate notion, right? You want to like, for a given S, there's some notion of witness of hardness. And if your function has hardness at least S to the 10, then the witness must exist. And if the hardness is less than S to the 1/10, then there won't be a witness. I mean, you'd be totally fine with an approximation. I don't know. I mean, because that's where I came from, right? I was trying to understand if you can even construct, or for what models could you construct like a notion of witness of hardness. And it's not, I mean, it's not obvious at all, because for instance, now we have this result for AC0. Okay, so AC0 MCSP, we have it didn't come out, right? Like I said, Rahul is going to publish its beautiful, really beautiful paper. That's going to come out hopefully this year. And this is hard to approximate, maybe up to a constant. And in fact, it's AC0 formulas. So the problem is, I give you the truth table of a total Boolean function, a single bit output Boolean function, and some value D. And I'm asking, what's the size of the smallest AC0 formula that computes this function? And it turns out that it's hard to approximate up to some factor, even super constant factor, not very high. Okay, so then you expect, well, if for such easy computational model, MCSP is hard to approximate, then for harder computational model, then MCSP should just be even harder to approximate, right? That's what you'd expect. But it turns out that it doesn't work like that at all. So for instance, for communication complexity, partial functions are hard to approximate. That's actually our result. The deterministic communication complexity of partial functions is hard to approximate, but the discrepancy of partial functions, and discrepancy corresponds to communication complexity of much more powerful model, right? So Fresnel protocols or whatever. That's actually, you can approximate it in polynomial time up to a factor of 8. So it's not obvious that just because it's hard to approximate on a weaker model, it will be hard to approximate on a stronger model. You know, my dream is that actually one day, my dream is actually that MCSP is, that you could approximate MCSP in CoNP, right? That's actually, like, I've had several quarrels with my co-authors because of this, because they don't believe it. They believe that MCSP is NP hard. But I hope not, actually. So if MCSP is, at least some approximate version is in CoNP, that actually means that, you know, we finally know, we could say something like a lower bound for a function looks like this. It's this kind of object that witnesses it's some duality for circuit size that you're after. And maybe it doesn't exist, but so I think it would be just so nice if it existed that I'd like to believe that it does, but I don't know. So I'm not in the, I guess my point is that I'm not. I'm hesitating to believe that MCSP is NP hard. I'd much prefer if it weren't. So I would rather, as long as I can, I believe that it's not. So.
So you mean the approximating MCSP?
Yeah, approximating. Let's hope that approximating MCSP.
No, but what I asked, imagine that somebody will say that your technique can be easily modified to prove that exact circuit size is hard and be hard, not for multi-output Boolean function, but for one output. Would you be surprised or
I would be incredibly surprised. My mind would explode.
So this idea of using multi-output things seems to be crucial somehow.
Yes, because it's actually controlling. It's actually controlling for the big thing that we don't know how to do in complexity theory. Using this multi-output, you can control how the circuit needs to behave. You can say something like, well, the circuit needs to be doing this. In our case, we can say that if you have a circuit for T and these DNFs, then the circuit has to look like this, right? It has K of these gates. We know what they are. They're the gates of the DNFs. That's like such a super strong statement. That is the holy grail of complexity theory, that we have a trick to be able to say something like that.
Yeah.
But like in general, we have no idea how. Give me a circuit for any function. Tell me anything that the circuit must be doing along the way. We have no idea, right? But with the strict, we can do it. And that's exactly what we're controlling for.
Yeah.
Or maybe you can try to decrease K bit by bit and then go from exact to approximate CSP.
All right, so I can make the claim. So if you can prove this result where the number of output bits is sub-exponential in n, right? So here we can prove it. So here, let's look at this function f. It's a multi-output function where we have some n. Actually, I've called it m there. But, the number of bits in the output is actually exponential. Sorry, let me turn this off. I don't know what this is. So the number of bits in the output of this multi-output function is exponential in the number of bits of the input. Prove something sub-exponential, and I'm already like, I have no idea how you do that. Like, because again, the size of the DNF, of course, is exponential, right? So I'm at a loss already, like how you do something like that. So, like improve on the size of n, even to be like, I don't know, 2 to the n by 2. Oh, no, I guess 2 to the n. Yeah, square root of 2 to the n. I'd be like, if the number of bits of the output is 2 to the n by 2, I'm already like significantly impressed. If you could do like 2 to the little of n, I would be very impressed. I know maybe there's some trick to get the over 2 there, but like much better. No, I don't know. Then I would guess you'd need something completely new. I don't think it exists even. I mean, I think. Yeah, like we can only prove that MCSP is hard for models for which we actually know how to prove lower bounds. So, yeah.
Yeah, okay. So who is the seminar leader? So somebody should ask whether there are more questions and thank the speaker. But where are the...
Yeah, so let's thank the speaker. I think if there are questions, people will ask.
Yeah.
But let's thank the speaker. We can, yeah. There are some
maybe we can, yeah. But maybe we can also at some point hear the other two parts, especially if they are simple. So if I have a kind of...
They're very, very simple.
Yeah, it's even better.
Okay, fair enough.
Yeah, we have some slots in June, or we can take it to our seminar as well.
Whenever you like. So there's like ongoing work, and yeah, I don't know if I should say this, but so there's ongoing work like on proving more communication complexity, hardness of computing communication complexity, like measures with Rahul Ilango and Ryan Williams and Swishi. Hiragana. So there will be some other paper that will be coming out later this year.
So that's an argument to postpone it till June, when you can tell more about the other.
I don't think June is soon enough. Is early enough. But I can show you these two arguments.
Okay, let's have this.
Whenever you like, yeah. I don't know. So the thing is that I feel that I could probably tell you in one page, but
no, it's always good if the talk is short. Nobody complains. It's never. I never have seen any complaints of this type.
Okay.
Especially if it's online, there is no harm, because if you have to travel to other university for 1 hour and return, and the talk is 10 minutes, it's annoying. If it's online, everyone is happy.
Okay.
Thank you for your talk. So let's finish the seminar.
Yeah. Thanks, guys. Thanks.
It's recorded, yeah?
Bye.
Yeah, it was clear.
Yeah, right.
Yeah. So maybe one can put them online as to make a tradition.
Yeah, I will ask Bruno offline whether he doesn't mind if you put it online. Or maybe you don't mind, so we can put it on YouTube.
Yeah.
Okay, good.
Only people who left have obstacles, but that's their problem. Okay.
Okay, goodbye. So I'm finishing the meeting.
Yeah, thanks, guys. Bye-bye.